Think about your morning coffee for a second. That simple act, pouring hot water over ground beans, it's actually governed by the very same principles that decide how we can store carbon deep underground, or even how we can grow new bone inside the human body. So let's dive into this hidden world, shall we? See, it's all about an architecture of nothingness, a maze of empty spaces. This invisible network is in the paper filter of your coffee maker, it's in the soil under your feet, it's even in the sponge you use to wash dishes. It is literally everywhere, controlling how fluids move in ways we barely ever stop to think about. So, what is this fundamental structure? What's the common thread that connects geology, biotechnology, and even clean energy? What's going on here? Well, the answer is something called a porous medium. And honestly, it's a beautifully simple idea. Just a solid thing that's full of holes. But as we're about to find out, the nature of those holes, their size, their shape, and how they're all connected is one of the most important and surprisingly complex fields in all of modern engineering. Okay, so to really get a handle on this, we need to learn the language that scientists use to talk about these voids. It's really all about finding a way to measure the nothingness that makes everything else work. Now, this is maybe the most important slide, because it highlights the huge difference between two key ideas. First, you've got porosity. That just tells you how much empty space there is. Think of it as the storage capacity. But then you have permeability, and that tells you how well connected all that space is. You see, you could have a rock with tons of holes, really high porosity, but if those holes don't connect to each other, nothing's going to flow through it. So permeability, that's the real measure of how efficient the flow is. And that path is never, ever a straight line. Fluid particles have to navigate this microscopic maze, winding their way around solid bits of material. We actually have a name for this. It's called tortuosity. The higher the tortuosity, the longer and more twisted the journey is for the fluid. And all that extra travel creates resistance and just slows everything down. And, it gets even more complicated from there. You have things like anisotropy, which just means flow can be way easier horizontally than it is vertically, like in a layered rock. Then there's effective porosity, which is a reminder to only count the useful pores that are actually connected. And you even have to think about the specific surface area, which is vital for things like filters, where you need chemical reactions to happen on the surfaces inside those tiny little voids. So how in the world do we put all of this together into a formula that we can actually use? Well, for that, we need to go back to the 19th century, to France, and to a very practical problem, getting clean drinking water. Right, so it's 1856, and this engineer, Henry Darcy, is tasked with designing sand filters to purify water for the city of Dijon. And through all of his experiments, he just stumbles upon this simple, really elegant relationship that would become the absolute bedrock principle for this entire field. And this is it. This is Darcy's law. Now, I know equations can look a little intimidating, but this one tells a very, very simple story. All it's saying is that the flow rate, Q, is determined by just a few key things: the properties of the material, the size of the area it's flowing through, and the force that's pushing it. Let's break that down. Let's just think about this in plain English. First, the harder you push on the fluid, so a bigger pressure difference, the faster it's going to flow. Makes perfect sense. Second, the longer the path the fluid has to take, well, the slower it's going to go. And finally, the material itself obviously matters. That's what the K stands for, hydraulic conductivity. It kind of bundles up all the properties of the fluid and the medium into one number that tells you the total resistance to flow. And this is why Darcy's law is such a big deal. It's basically the F equals ma of hydrogeology. It's that foundational rule. And what's really incredible is that even today, with all of our supercomputers, this simple equation from the 1800s is still at the heart of our most complex models. It gives us this incredibly powerful tool to predict and control all of this invisible movement happening around us. Okay, so we've got the theory. But why does any of it matter? Well, because understanding and, more importantly, manipulating this invisible network is actually the key to solving some of the biggest challenges we face today. And the applications are just unbelievably diverse. I mean, look at energy. We're trying to inject CO2 into basalt rock to store it forever. But as the CO2 turns to mineral, it can actually clog up the very holes we need to use. Or in biotech, we're designing these porous scaffolds to regrow bone, and they need pores that are big enough for cells but small enough to be strong. Or even in fuel cells, you have a porous layer that has to let hydrogen in and let water out without getting totally flooded. Let's just stick with those bone scaffolds for a second because the precision here is just incredible. Research has shown that for bone-forming cells to do their thing, to grow and create blood vessels, the absolute best pore size is somewhere between 100 and 400 micrometers. I mean, too small and nutrients can't get in. Too big and the whole thing is just too weak to work. And hey, remember anisotropy? This chart is the perfect way to see it. In a layered rock like shale, the permeability can be thousands, even millions of times higher along the horizontal layers than it is vertically across them. And that is absolutely critical for things like oil and gas, where you have to know which way the fluid is going to want to go. So where is all this headed? Well, the future isn't just about understanding the porous media we find in nature. It's about designing and engineering brand new ones with properties we've only dreamed of. We are moving into a pretty incredible new era here. With digital rock physics, we can build these amazing 3D models of pore networks on a computer and just run thousands of virtual experiments. We're creating biomedical materials inspired by nature that can separate oil and water with almost perfect efficiency. And we're even starting to tackle the ultimate challenge, materials that actually change and evolve as fluid flows right through them. When you boil it all down, it comes to this. The empty spaces are every bit as important as the solid stuff. Mastering the physics of what happens in the pore space is absolutely fundamental to everything from sustainable energy and clean water to the future of regenerative medicine. So the next time you make a coffee or just walk across a field, maybe take a second to think about that invisible network. It's this hidden world of just immense complexity and, really, of opportunity. So the real question is, now that you know it's there, what are you going to do with it?